So hello, let us start our sixth lecture. And if you remember, in our last lecture, we have told you how to develop the equivalent circuit first of an ideal transformer, and then how to transform the impedance of an ideal transformer from secondary to primary, and also how to draw equivalent circuit of an ideal transformer with respect to the secondary side. Then what we have started is that this ideal transformer is of course quite different from a practical transformer. In practical transformer, for example, there will be a iron core whose permeability is finite. Winding resistance will be present. Leakage fluxes will be present. So that is called a practical transformer. So we are now bringing those realities into that equivalent circuit of the ideal transformer one by one. So we have first decided that if mu r is finite, how to tackle this situation. And if you remember, we have done it like this. This is suppose a practical transformer where we have considered, just I will go very quickly, this is the Z2 secondary load, and if it is a practical transformer, if you apply a voltage here, then and when the switch is open, it is under no load condition, secondary is not carrying any current, and if you connect an ammeter here, we have seen that it will draw some current to establish the flux. And this is a practical transformer. The equivalent of this one, this can be that this is the supply, and then you connect a reactance which is not to be confused with the winding of the transformer, and then as if the ideal transformer is present. This portion is ideal transformer. So a practical transformer becomes equivalent to a reactance connected across an ideal transformer on its primary side when you want to consider mu r to be finite, when you want to take that into account. And this we have seen that it satisfies all the known things that we have discussed. For example, when the switch is open, ammeter will read V1 by Xm. Why it is represented by a reactance is quite obvious, because the magnetizing current will be lagging the supply voltage by 90 degree, the direction in which the flux is developed. So it is represented by a reactance, and this Xm is called the magnetizing reactance of the transformer. Magnetizing reactance of the transformer. So this portion I told you is your ideal transformer, and this whole thing is your practical transformer. I mean somewhat practical transformer. And this one is your ideal transformer. And when you load it, the moment you load it, this ideal transformer will carry appropriate reflected current I2 dashed for a current of I2 on the secondary side, and this current is always constant, decided by V1 by Xm, 90 degree lagging with respect to V1, and this will decide the total current now, I1 bar. So how the phasor diagram will get now modified? This is the phi. The induced voltage on the secondary side will be E1 and then E2. Suppose it is a stepped up transformer, and the secondary load is suppose inductive in nature, say RL load. Then the secondary current will be your I2. the angle by which it will lag this voltage E2, remember this is E2, this is E1, will depend upon the power factor of the load theta 2, and primary reflected current I2 dashed here will be, I will just draw opposite to this one, I2 dashed, and total current recorded or drawn from the supply will be the sum of these two currents. So you have to add these two in vector form or phasor sum, and you get the current drawn from the primary. This will be the relationship. Remember that I2 dashed into N1 is equal to I2 into N2. And obviously, strictly speaking, I1 N1 will not be equal to I2 N2. However, in practice, as I have told you, this magnetizing current will be what percentage of the rated current? About 2 to 3% of that one. So for all practical calculations, or say in the laboratory for testing purposes, you forget about that small change in current to decide upon the ratings of the ammeters to be connected to carry out a particular test. Okay, so but this is true. I2 dash N1 is equal to I2 N2, and I1 N1 will be, perhaps it is better to tell, close to I2 N2, very close to I2 N2, because of the fact Im itself is quite small. And also you know that the input power factor this time is not same as the load power factor connected across the secondary of the transformer, for obvious reason. So total input power will be V1 I1 cosine theta 1. Of course, the extra current that Im, it does not consume any power, etc. Those are valid. So this will be the phasor diagram of this somewhat ideal transformer under both no load and load condition. Under no load condition, I2 dashed disappear. It is only Im which is left in the circuit. So this is the equivalent circuit. Okay. General equivalent circuit. Now if I want to draw the equivalent circuit referred to primary of this transformer, equivalent circuit referred to primary, this will be what? I think you have done, I have told you to complete this one. This will be, this is XM, AXM will be there. It is reactance, not transformer coil. Once again I repeat. And this one will be an impedance connected. What will be the value of this impedance? A square Z2. Because for ideal transformer this is true. From this impedance will appear here. And this will be, and this I will show as the I2 dashed. This I will show as Im, and this I will show as I1. This will be V1. Where A, once again, note that N1 by N2. So this is the equivalent circuit referred to primary. What will be the equivalent circuit referred to secondary? Circuit referred to secondary. Tell me. So in the secondary circuit, now I am transferring. One thing I should make it clear. Suppose you have drawn the equivalent circuit with respect to a particular site already. For example, here I have drawn with respect to this one. Now to decide upon the equivalent circuit, how it will look like with respect to the other side, I can as well start from this equivalent circuit now. Remembering this thing, that whenever any impedance is transferred from the secondary side to the primary side, it should be multiplied by S squared. That is, in this particular case, look here, the impedance here, with respect to this one, actually is Z2. This Z2, its representation on the primary side will be how much? A square Z2. That is, suppose you want to transfer quantities from secondary to primary. Just I will quickly tell, secondary to primary. Any impedance should be multiplied by A square. Any current should be divided by I2. I2 dashed you get by what? Actual current by A. And any voltage? A into V2. You have to multiply the actual secondary voltage with A. Then you get V1. V2 by N2 into N1. Now, similarly, if you want to transfer any primary impedance to the secondary side, what you should do? You should divide by A squared. So, any impedance on the primary side should be divided by A square. Any current, if you transfer it to the secondary side, should be multiplied by A. Are you getting the opposite thing? That is, if you divide by A square, you get Z2. So, suppose with respect to primary, I know the impedance. It should be divided by A square. Current should be multiplied by A. And voltage should be divided by A. So, what I am trying to tell, once I have got the equivalent circuit, refer to the primary, the drawing of equivalent circuit, refer to secondary, can be done in this way. What will happen to this voltage? What should I do? I should divide it by A. V1 by A I should write. What should happen to this reactance? This I should divide it by Xm squared. Reactance is an impedance. What should happen to this impedance? A square Z2 by A square. That is Z2. That is what I expect. That is A square Z2 by A square. So, one can reach at this equivalent circuit also from there, because what will be the voltage between these 2 points? A square Z2. And then this magnetizing current, something is drawn from the supply, so that should be shown in parallel, and then your Z2 is Z2. So, this is the equivalent circuit of the transformer. Refer to the secondary side. So, suppose at your disposal you have drawn your equivalent circuit with respect to a particular side. Don't try to go via this path once again to draw the equivalent circuit with respect to the other side. That is just a trick. So, this is this one. So, this way one can form the equivalent circuit. And another thing I told you, that this magnetizing reactance Xm should indeed be divided by A square. Because of what? Because physically, if you look at, no matter whether the transformer is energized from the primary side or the secondary side, phi max remains same. If phi max remains same, the current MMF necessary to establish that flux remains same from this side if you energize or from the other side. But turns are different. Therefore, this Xm2 gets divided by A square, such that the current will be in that ratio, magnetizing current also. So, that allows us to represent, to bring this parallel impedance also in this fashion. Yes, anything you are asking? Current. This one, this is not Im. This is then I2, actual current, secondary side. Which will be how much? I2 dashed by A. This current gets transformed to, you have to divide, multiply it by A. So, you get I2. This voltage, you divide it by V1 by A. That's all. Clear? So anyway, we will calculate the equivalent circuit at various levels. Let me further proceed, then I will tell.
If the flux is constant, sir, how can the MMF be constant, sir? Because the reluctance will be different.
How reluctance is different?
The number of turns will be different.
Magnetic circuit, the path through which the flux flows, that reluctance is constant. I am not changing the magnetic circuit. Am I changing? What is the expression of the reluctance that I have done in the first class? It depends upon the mu of this material, cross-sectional area of the core, length of the magnetic path, etc. That you kindly go through it. Achha, then this is there. So this is so far the equivalent circuit of the transformer referred to either side, taking magnetizing current into account. That is important. Now I will bring into another real things into the transformer. That is the core losses. So far we have assumed no core loss. There is no core loss is present in the transformer. Now before really I go into this, I will just have a quick review of the core losses. Core loss occurs inside the core of the transformer. Okay, that is the magnetic material of the transformer. There the core losses occur, and that is a magnetic core. That's why it is called core losses. Core losses comprises of two things. Is equal to, there will be some eddy current loss plus some hysteresis loss. I will quickly now tell you eddy current loss occurs because of what reason and what is its approximate expression. Similarly, hysteresis loss, how does it occur in the core of a magnetic material and how it can be calculated. Okay, so let me first do eddy current loss. Whenever a magnetic material is subjected to a time varying field, some voltage will be induced in the core. In the same way, the voltage is induced in the various turns of primaries and secondaries. For example, you consider some solid core, magnetic core material like this, and over which let us assume you have some number of coils wound like this. Like this, and it is suppose a magnetic material, solid magnetic material, solid suppose. Now if this coil is energized from a single phase supply, then the flux will be produced along this direction. Of course it will sometime go from left to right or from right to left, and its value will change with time. And if any other coil is wound on this same magnetic structure, we know there will be induced voltage that can act as your secondary. But let us for the time being forget about other coils. Now if in this core of this material you consider any closed path, through this area there is a change of flux density. Okay. So in this closed path there will be induced voltage, as there is induced voltage on a single turn of a coil. That is, you imagine that suppose this is the core of the transformer. There is induced voltage. I mean, this is energized. And on the secondary, let us imagine you have a single turn. And there is a switch here. Now, how much voltage is induced in this one? It is N phi dt, the amount of flux which is crossing perpendicular to the plane of that coil. This is phi. What is the value of the phi? B max into this area. That is the area enclosed by the coil. Now, in this particular case, it so happens that this coil, imaginary coil, because iron is a conducting material. So, this imaginary coil is already closed by a switch. You don't have any control over it. That is, the situation is like this, as if there is already some secondaries present which are closed onto themselves already. So, there is some induced voltage and the circuit is completed on the I mean, something like secondaries of a transformer is already loaded. So, if you suppose consider this is the core of the material, once again I am telling, you consider any arbitrary closed path which is made of conducting material, that is iron. Now, what I am telling, in this circuit, in this coil, imaginary coil, there will be induced voltage or not? Tell me what will be the magnitude of this induced voltage? It will be, RMS value of the induced voltage will be how much? Root 2 F phi max. This phi max will be how much? B max, flux density in the core, into only this area. That is very important. How much flux is linking this particular coil which I am considering? It is the flux density into this area. In case of all the secondary turns, all the turns are wound wrapping over the whole area of the secondary. So it is B max into some constant area that is there. But if you consider any imaginary coil here inside this one, a closed path, the induced voltage in that single turn will be root 2 pi F B max into what I am trying to tell, this area will be the flux. Say some AC, whatever it is, AX, you call it AX. This area is AX. Into what? N is 1. This much induced voltage is there. But this induced voltage in this coil is, the switch is already closed. So this induced voltage, why not it will drive some current here? Induced voltage, suppose you imagine this imaginary path is somewhat open, I have closed it, then some current will circulate. As you load the secondary of a transformer, current starts flowing. So there will be some current flowing now in this loop. What will be the magnitude of this current? This voltage divided by the resistance of this path. Let us assume this path is resistive. That much current will flow. And when that current flows in this path, only a single path I have yet considered, there will be I square into the resistance of this path. That amount of loss will take place. And not only that, the moment this carries current, it tries to disturb the flux inside the core, which in any case primary will try to counteract. So what will be, how the primary will react to this one? It will draw some extra current to compensate for this extra MMF, which tries to disturb the level of the flux. And this is true for any path you consider. There will be several paths like that, and all the path will have induced voltage, and all the path is closed onto themselves already. So there will be some current inside this one core of the material, and this will definitely produce some heating effect inside the core of the transformer. So these currents which flows because of the induced voltage in the core is called eddy currents. Eddy currents. So eddy current will be flowing inside the core in a plane which is perpendicular to the direction of the field. What is the direction of the field? I have assumed into the paper, out of the paper, like this it is doing. Direction of the flux. That is, flux is moving like this way, time varying field. And the current will be sometimes flowing this way, AC current in the usual way. So there will be some power losses taking place. Now we want to show you on which factors this power loss will depend upon. Obviously, one can imagine if it is a solid, without doing any mathematics. Suppose this is a solid core of iron. These will be the eddy current paths, which I am not drawing. Now, if you are asked how to reduce these eddy current losses, one thing, suppose you compare this core and another core which has got this much thickness. Do you think eddy current loss will be more here or less here? Because the current flow is restricted in a very small area. Are you getting? So instead of using a solid block of iron, what you do, suppose you take several thin plates and stack them together to get this breadth or length, whatever it is. So you can realize this section, instead of using a solid block of iron, by thinner plates. And this one I am getting, not doing any mathematics, just by using my common sense. Okay, the solid block of iron, there will be lot of eddy current losses, understood. Now, this can be perhaps reduced if I use thinner plates. Why? Because the path of the eddy current flow will be small. In fact, if you imagine this is brought down to a very low thickness thing, eddy current will practically not exist. However, one point should be very clearly understood. Whenever you talk about many plates stacking together, each plate should be electrically insulated from the other. Then the moment they are not electrically insulated, it is same as this one. Because the current will now then flow once again over the whole area. In fact, these are, suppose what I want to say, suppose this top is not there. You imagine it is like this. This one is your structure, magnetic structure. You could, and what is the cross-sectional area? It is this cross-sectional area. You could use a solid block of iron to make this complete iron structure. Instead of that, you are using some plates of very small thickness, and you stack them together. Then this area can be realized, which you are getting by using a solid block of iron. And what I am trying to tell, each plate from the other plates, they should be insulated. Generally, they are given a varnish coating to insulate them from one another. The color of such plates will be like this. Some varnish coating is there. It is iron plate. Some varnish coating is put and they are stacked together. So the point is, important point is that now that the plate should be made thinner is understood. there is no other way out. Otherwise, there will be tremendous heating effect inside the core of the transformer. Now, with this understanding, we will now show you on what factors this eddy current will depend. Suppose, so what we do is this, eddy currents loss in thin plates. In thin plates. Of course, the diagram I will draw in a bigger scale to derive some important thing. I will draw in bigger scale. Suppose this is the thickness of the plate, and this is a plate. This is the plate. I mean, it continues like that. Suppose this is the plate. Now, this material is suppose subjected to a time varying field Bt along the axial length, that is, suppose this length is L. Parallel to L, the field is acting. Or in other words, this B is perpendicular to this surface. Suppose let us call it some A, B, C, D. I think this you have understood. So the flux is along L, that is, it is perpendicular to any vertical cross section you draw. So it is subjected to this time varying field. Suppose the thickness of the plate is tau, and height of the plate is h. Height of the plate is h. Remember, plate thickness is quite small compared to the height or length of this one, because we are restricting our attention to thin plates only. Then on what factors it depends. That is the idea. Now, to calculate the expression for eddy current loss, what you do, you find out the midpoint of this one, call it 0, and consider a small path like this. This path you consider at a distance x with dx thickness. You consider a strip, a closed path. I want to find out what is the induced voltage in this single turn. Suppose the flux density, maximum value of flux density, that is Bt, is Bmax. So in this element, that is in this path, dx is an elemental distance which is very small, close to 0. How much will be the induced voltage in this red closed area? It will be E, if I call it, how much? Root 2 RMS value of the voltage, root 2 pi f. What is phi max? Bmax into this inside area. So Bmax is Bmax, and inside area will be how much? Twice x into h. Twice h into x. Dx is sufficiently small. What you will gain by doing that? You must have that calculus background. Okay? Okay. So this area inside this one will be very close to this one, twice h into x. Okay, let me first proceed. The flux is flowing like this. So this area I have to take. In a suppose coil, any coil whatsoever. I want to find out what is the induced voltage in the coil. What you will do? You will first see perpendicular to the direction of the plane of the coil, how much is the flux flowing. So this is this one, perpendicular to this area. What is the amount of flux crossing that area? That will be Bmax into twice h into x, twice x into h. This will be the induced voltage in that. Okay. Now, what will be the path of the current? Path of the current will be, for this closed path assumed, it will be flowing like this. And it will flow all along those turns. This turn, electrically, this will flow like this, all along the length of this one. Okay, some current will flow. So, I want to find out, this is the induced voltage, the path is known through which current will be flowing, how much will be the power loss in that. So, power loss in that elemental thing should be P, elemental power loss in that elemental path. Very simple calculation, nothing great. Will be how much? B square by R, if you assume this path is fully resistive. That is, this E square divided by the resistance of the path. Now let me hear from you, what should I write for the resistance of the path? That is, rho L by A is the resistance of the path. Don't answer all of you, but if somebody is confident, please tell me. What should be my L? What should be my A? To calculate this will be square, B square by R. Then one of you tell.
The A should be capital L dx.
A will be rho A. See, this is the current will flow like this.
Dx into L.
Right. Current will flow like this. This is the path. I mean, it is within this one. So, it is this cross-section area through which current flows, I. Like this. All along this length. So, cross-sectional area is L into dx. And what should be the length? Length should be the perimeter of this one. That is twice h plus 2x plus 2x, 4x. Is that clear? Plus 4x. This will be there. Now the next step when I will do, don't shout. Because of the fact, I am calculating the eddy current loss in a very thin plate. And I am trying to see, then thin plates I will be using. On what factors now eddy current depends. See, this one, if you consider a plate like this, the plate like this, this plate like this is suppose H. What is this thickness is tau. Thickness is tau is this much is thickness tau. Now, compared to this thickness, this tau, this x here, x will be also small. Within tau only it will come, x, dx, whatever you consider. This one, that is tau, if it is sufficiently smaller than L or h, those dimensions, h, smaller than h, if tau is much smaller than the h, the height of this one, I can write it as, I will refer to this diagram once more. The elemental power loss will be E square, that is root 2, I mean this I can straight away write, 2 pi square f square Bmax squared, then 4 h square x square divided by, what I am trying to tell, this earlier one will be approximately equal to rho twice h by LdX. This should be understood because of the fact tau is much smaller than your h. So the length of the current flowing is practically the two heights. Is not? What is the current path? H, then this small tau, this h. What is the perimeter difference? Whether you add that 2h or not, that 2 tau, it does not matter. Okay, so with this one, that is eddy current loss in a thin plate, let us assume tau is much smaller than this height. When you neglect something with respect to some other quantities, we are verifying. So it will be like this. So this one, with this assumption here, this will then become 8 pi square f square b max square pi square f square b max square 2 4 I have taken, and you do this is simple mathematics, you do it. So this one, so this h, one h goes here, one h will there, and below it will be twice rho and L x square dx. If some term is missing, you tell me. Everything is okay? All terms are. So this will be the loss in this element. Now suppose I want to calculate over whole surface how much will be the power loss. What you have to do? You have to integrate it. Tell me the limits of integration. 0 to tau by 2. That is correct. Only from this to this. So the total loss, total eddy current loss, total eddy loss will be, I think this will be 4 pi square f square b max square. HL is constant by rho, and this will be integrated from x equal to 0 to tau by 2 x square dx. So this thing will be 4 pi square f square b max squared HL by rho into tau cube by 8 by 3. Okay, x cube by 3. So this will be there. Now this one I will write it like this. So eddy loss will be some pi square f square by 6 rho, and then b max square, then tau square, and then h L tau. This way I will write. What is HL tau? It is the volume of the material. Okay, volume of the material. So I can write it like this: eddy current loss. I am writing per unit volume will be equal to this. There will be rho also. I am missing. Rho is there. Pi square f square. Some 6 rho b max square tau square. Per unit volume it is like this. Therefore, per unit volume of the eddy current loss, it will depend upon, for thin plates, this I remind you once again, this formula will not hold good for a big plate like that, this one. If you apply, you are gone, because it it depends upon this crucial approximation that thickness is so small, I can neglect this 4x compared to this 2h. That is there. Because I know I have to make the plates thinner. In fact, transformer plates are used of thickness 0.35 millimeter or so. This I will tell you in great detail after, when I take up construction of the transformer. So it is like this. Per unit volume it will be like this. So it depends upon the square of the maximum value of the flux density. It depends upon frequency square, supply of the frequency square. And it depends upon the thickness square at that low level of thickness. And also it depends upon the resistivity of the material which is used to construct the core. Obviously, one should see this eddy current loss should be as small as possible. You should try to use higher resistivity material. Like that. So this you just remember. This is the expression for the eddy current loss per unit volumes, and it is directly proportional to the square of the frequency and maximum value of the flux density squared. It is like that. Now, what is hysteresis loss? Very quickly. This you must have read, I suppose, in your first year class. Something. Hysteresis loss. Now, hysteresis loss is something different. You should understand it in this way. Now, what happens is this: when a magnetic material or core is subjected to alternating field, then the magnetic domains or molecules, in whichever way you look at the magnetic theory, they will also orient themselves at one time in a particular direction, in the other half cycle it will be in the opposite direction. That is the Webster's north-south theorem. External field, whatever you apply, it will try to align along that. But that field itself is changing its direction. So each molecule or domain will try to align sometimes from, if you look at this diagram, suppose this is the flux. Sometimes all the molecules will be north-south like this. And in the other half cycle it will be just opposite. It will as if rotate like that. That way the domains or molecules get changed every half cycle. Because of that, there will be friction at that level. So there will be some heating effect in the core. That is the primary reason of this hysteresis loss taking place inside the core of a material. So there will be also some wattage loss. That is the effect of both eddy current and hysteresis loss can be felt if you touch the core. Core will become hot. Okay, no matter whether there is winding or not. Other secondary winding or not. Core itself carries some current because of eddy current loss, and because of the orientation of these domains in every half cycles, there will be some power losses. This is called hysteresis loss. Now, how to calculate the hysteresis loss? This is somewhat tricky. Tricky in the sense one should understand this and keep this picture in mind. Now, this I will take another page to explain this one. Suppose BH characteristics of a material, of a practical material, when it is excited by AC current, will be somewhat like this. This you know, I am sure. It will be somewhat like this. This is H, and this is B. Suppose you have a coil wound over a magnetic material whose BH characteristics is this one. Let us start from the very first point. that is when current is 0 and B is increasing. B is increasing. Now, when there is no residual magnetism, H will increase and B will increase like this. It will start from this point. Now, if you decrease current, because of retentivity, the path traverse will be like this. And if you now give negative current, that is, initially current was flowing like this, flows like this, then it will go this way. This loop is obtained in a BH material. Now, I want to find out whether there will be any power loss when such an alterations goes on in the current. So, current is alternating in nature. Now, after this one is over, and if you excite this H is what? Ni by L. Ln is constant. So, direction or frequency of the current will dictate how fast and to what extreme two values it will oscillate. So, after this is over, then it will go on tracing this path like this. When current is going 0, reaching maximum, this is suppose this could be as well my I-axis for a given magnetic material of N turns and L. So, if this is current, it is like this. Anyway, today I complete, and then